Hello, in this lecture we will find out the length of line segment X using two different methods. In the drawing we have a semicircle inside a quarter circle. We know that side AO equals to 6 units, and we also know that AC is tangent to this semicircle at this point. And we want to find out the length of line segment AC that is equal to X. So we'll start with the first method. Here, first of all, because of the fact that we are talking here on a quarter circle, A or B is a quarter circle, point O must be the center of the quarter circle, and then again A or B must be equal to 90 degrees. So we know that point O is the center of the quarter circle and point A is the point of the circle itself. And this is exactly the definition of a radius. That is to say, AO is the radius of the quarter circle that is equal to 6 units. Likewise, OB is also the radius of the quarter circle because of the fact that it starts from the center. Line segment OB starts from the center of the quarter circle, that is to say from point O, and ends at point B, that is the point of the quarter circle itself. And again, this is exactly the definition of a radius. So OB is the radius of the quarter circle, that is to say it is equal to also 6 units. But OB is not only the radius of the quarter circle, but it is also the diameter of the semicircle. So we know that the diameter of the semicircle OB equals to 6 units, therefore the radius must be equal to half of it. That is to say, the radius of the semicircle equals to 6 over 2 units. That is to say, the radius of the semicircle equals to 3 units. So here we will define the center of this semicircle as point P. And we will define the point of tendency of tangent AC with this semicircle as point D. So here OP will be equal to 3 units, PB will be equal to 3 units, and also if we join points D and P together by a straight line, PD is also the radius of the semicircle that is equal to 3 units. Okay, I repeat again, for the reason that all those line segments are the radii of the semicircle OP, PD and PB are the radii of the semicircle because of the fact that they start from the center of the semicircle, that is to say from point P, and end at any point on the semicircle itself, and this is exactly the definition of a radius. So OP equals to PD equals to PB, and they are all the radii of the semicircle, that is to say, they are equal to 3 units. In the next step, we will join points A and P together by a straight line. And I will present to you a new rule that is actually rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. The length of two tangents from a common external point to a circle are equal. So I will read rule number 1 again. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So what is the meaning of rule number 1? The meaning of rule number 1 is that if we have this circle and we also have point P, here this point P is defined as an external point of this circle. Why point P is an external point of this circle? Because point P is not located inside this circle, nor on this circle, but it is located outside of this circle. Therefore, point P is defined as an external point of this circle. So if from the point P, that is the external point of this circle, we'll draw two tangents to this circle, then the first tangent will be this tangent as the point of tangency of the first tangent with this circle will be defined as A. So AP or PA is the first tangent, and we will also draw a second tangent to this circle. We will define the point of tangency of the second tangent with this circle as point B. And according to rule number 1, the lengths of two tangents, that is to say, the length of the first tangent is PA, and the length of the second tangent is PB. So according to rule number 1, the lengths of two tangents from a common external point, that is to say, from point P that is defined as a common external point to a circle, 2 points A and B are equal. That is to say, the length of those two tangents are equal to each other. That is to say, PA equals to PB, according to rule number 1. So whenever you draw two tangents to a circle from a common external point to that circle, then the lengths of those two tangents will be equal to each other. In this case, PA equals to PB. So we can implement rule number 1 in our drawing, because in our drawing we have the common external point, point A. Point A is a common external point in relation to the semicircle, and from the common external point, point A, we have two tangents to this circle. The first tangent is tangent AO, and the second tangent is tangent AD. And according to rule number 1, the lengths of those two tangents must be equal to each other. That is to say, AO equals to AD. So I write it down. According to rule number 1, AO must be equal to AD, again, AO must be equal to AD according to rule number 1. But AO equals to 6 units according to what is given us in the question. So can I tell that AO equals to 6 units? And from this equation, 6 equals to AO equals to AD, we will derive that AD is also equals to 6 units. Okay, so here AD equals to 6 units. In the next step, we will prove that those two right triangles can go into each other. That is to say, triangle AOP can go into triangle APD. So, we will prove that the right main triangle, triangle AOP, is congruent to the right main triangle, triangle APD. So we will actually prove that triangle AOP congruent. This is the sign of congruent to triangle ADP according to side rule. Okay. So why those two plain right triangles can go into each other? First of all, we just right now prove that AO equals to AD equals to 6 units. In addition, side AP is a common side, it belongs to both triangles, so we can write down that AP equals to AP is a common side that belongs to both triangles. And finally, OP is equal to PD, and they are both equal to 3 units. They are the radii of the semicircle. OP equals to PD equals to 3 units. So we prove that all the sides of triangle AOP can go into all the sides of triangle ADP. Therefore, those two right triangles can go into each other according to side rule. And from the fact that those two right main triangles can go into each other, we will conclude that those two angles are equal to each other. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be equal to each other. That is to say, angle OAP equals to angle PAD. Again, according to the rule that corresponding angles in congruent triangles are equal to each other. So if we define angle O, so here, angle OAP equals to angle PAD, and if we define angle OAP as theta, then we can write here that angle OAP equals to theta according to our definition. So then, according to this equation, theta equals to angle OAP equals to angle PAD, we will derive that angle PAD is also equals to theta. Okay, so this angle is also equals to theta. So those two angles are equal to each other, they are both equal to theta. In the next step, we will focus on triangle AOP. This triangle, the right triangle, triangle AOP. In the right triangle, triangle AOP, the right green triangle, triangle AOP, we know that tangent theta, in this right triangle AOP, tangent theta equals to OP over OA. OP over OA. Tangent theta equals to OP over OA. OP equals to 3 units. And OA equals to 6 units. So here we will divide both the numerator and the denominator of this side of the equation by 3, and we will get that 3 over 3 is 1 and 6 over 3 is 2. So in conclusion, we found out that tangent theta equals to 1/2. Okay? Tangent theta equals to 1/2. In the next step, we will join points O and C together by a straight line. So by joining points O and C together by a straight line, we created triangle AOC. Okay, we have here triangle AOC. So I will present to you the law of cosines, and then we will implement the law of cosines in this triangle AOC. So what is the law of cosines? First of all, the law of cosines is true in any triangle. So actually, if we have triangle ABC, that could be any triangle. This is triangle ABC. And we know that side AB of this triangle ABC equals to a unit in its length. And side AC equals to B units in its length. And side BC equals to C units in its length. And the angle between side AB and side AC equals to alpha. Then according to the law of cosines in this triangle ABC, we will get that C squared equals to A squared plus B squared minus 2 times A times B times cosine alpha. Okay? Again, C squared equals to A squared plus B squared minus 2 times A times B times cosine alpha. Okay? Now we will implement the law of cosines in triangle AOC. So I'll copy triangle AOC in this page and we'll implement the law of cosines in triangle AOC. AO equals to 6 units according to what is given us in the question. Angle OAB, this angle equals to theta plus theta, it is 2 theta. AC equals to X according to what is given us in the question, and this is the line segment that we are looking for. So AC equals to X, and what is the value of OC? Here O is the center of the quarter circle. C is the point of the quarter circle itself. So, and this is exactly the definition of a radius. This is to say, OC is the radius of the quarter circle that is equal to 6 units. So actually, this is triangle AOC that I copied from the original drawing. So according to the law of cosines, we will get here that this will be equation number 1, OC squared equals to AO squared plus AC squared OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. So I repeat again on question number 1. According to the law of cosines in this triangle AOC, we get that OC squared equals to AO squared plus AC squared minus 2 times AO times OC times cosine 2 theta. Okay. So here AO equals to 6 units. Therefore, AO squared is 6 squared, that is 36, plus AC squared. AC equals to X, so AC squared is X squared. Okay, AO squared equals to X squared plus AO squared, it is actually equals to 6 squared, that is 36, plus AC squared. AC equals to X, so AC squared equals to X squared minus 2 times AO is 6 minus 2 times AO, that is 6 times AC, that is X, times cosine 2 theta. So in conclusion, according to question number 1, we found out that 36 equals to 36 plus X squared minus 2 times 6 times X times cosine 2 theta. Okay, here we have 36 on both sides of equation number 1, so 36 will get cancelled. And what is left from equation number 1 after we cancel 36? What is left is actually here we have in the left side of equation number 1 we have 0. that is equal to x squared minus 2 times 6 is minus 12, so actually this expression equals to minus 12 times x times cosine 2 theta. Okay, so according to equation number 1, 0 equals to x squared minus 12x times cosine 2 theta. Here we will add 12x cosine 2 theta to this equation, equation number 1, and we get that according to equation number 1, 12x cosine 2 theta equals to x squared so 12x times cosine 2 theta equals to x squared. Here we will divide this equation, equation number 1, by x. I will remind to you that it is allowable to divide this equation by x, because here we can see that the moment that x, it is the length of line segment AC, therefore it must be a positive number. It can never be equal to 0, and for that reason it is allowable to divide the equation number 1 by x. So we'll divide the equation number 1 by x, and we'll get in this side of the equation x will get cancelled, and we're left only with 12 times cosine 2 theta. On the other side of the equation we have x squared over x equals to x. So the only thing that is left to do in order to find out the value of x, the line segment that we are looking for, is to find out the value of cosine 2 theta. Okay. In order to find out the value of cosine 2 theta, I will present to you trigonometric identity. According to the following trigonometric identity, cosine 2 theta equals to 1 plus tangent square theta over 1 minus tangent square theta. And we have already found out that tangent theta equals to 1/2 we have already found out that tangent theta equals to 1/2, so we can substitute tangent theta in this trigonometric identity by 1/2. We'll do it now, and we'll get that according to this trigonometric identity, cosine 2 theta equals to 1 plus tangent square theta. If tangent theta equals to 1/2, it means that tangent square theta must be equal to 1/2 squared. Okay, we have cosine 2 theta equals to 1 plus 1/2 squared over 1 plus tangent square theta, that is equal to 1/2 squared. So we know that 1/2 squared is 1/4, so here we get that cosine 2 theta equals to 1 plus 1/2 squared is 1/4 over 1 minus tan square theta is minus 1/4. Okay, so cosine 2 theta equals to 1 plus 1/4 over 1 plus 1/2 square is 1/4. So actually the trigonometric identity is tangent cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. So here we have 1 plus 1/4 over 1 minus 1/4. So according to this trigonometric identity, we will get that cosine 2 theta equals to 1 plus 1/2 is 5. 1 plus 1/4 is 5/4. It's actually 1 minus 1/2 is 3/4 over 1 plus 1/4 is 5/4. So here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled. In conclusion, it found out that cosine 2 theta equals to 3 over 5. Okay, cosine 2 theta equals to 3 over 5. Now we can substitute cosine 2 theta in equation number 1 by 3 over 5. We will do it now according to equation number 1. 12 times cosine 2 theta equals to 3/5. 12 times cosine 2 theta equals to x, of course. Okay, so 12 times cosine 2 theta equals to x. We'll substitute cosine 2 theta by 3/5. And we get it according to equation number 1. 12 times cosine 2 theta is 3/5 equals to x. So here 12 times 3 is 36 over 5. And x equals to 36 over 5, that is 7.2 units. So I found out that x, that is actually equals to AC also, equals to 7.2 units. That is the answer to the question. So we can write here that x that is equal to AC equals to 7.2 units. We finished with the first method. In the next step I will present to you how to find out the length of line segment AC that is equal to X according to the second method. In the second method, we will use all the things that we have already found out in the first method. Here we have already found out that this angle is a right angle, point O is the center of the quarter circle, and the radius of the quarter circle equals to 6 units. This is point P, the center of the semicircle. Point D is the point of tendency of tangent AC with this semicircle. And there we have already found out that OP equals to 3 units, PD equals to 3 units, and also PB equals to 3 units. All the line segments that I mentioned are the radii of the semicircle that is actually equals to 3 units. Then we connected points A and P together by a straight line. And we already found out that AD equals to 6 units. And here those two triangles can go into each other. Triangle AOP can go into triangle APD according to side rule. And therefore those two angles are equal to each other, they're both equal to theta, according to the rule that corresponding angles between corresponding angles in congruent triangles are equal to each other. Okay? So from this stage, from this step, we'll continue according to the second method. All those things we've already done in the first method. Here we'll do another thing. We will extend line segment AC and also line segment OB by a straight line until they intersect with each other. I repeat again, we extended line segment OB and line segment OC by a straight line until they intersect with each other. We will define the intersection point between the extended AC and the extended OB as point E. Okay. The intersection point between those two line segments is defined as point E. So in this way, by drawing those two line segments, by extending those two line segments, we created the right triangle, triangle AOP. AOE. Actually, this is the right triangle, triangle AOE. In this right triangle AOE, we know that AP, line segment AP divides angle OAE into two equal parts. That is to say, line segment AB divides angle OAE into two halves. And this is exactly the definition of angle bisector. So OAP is the angle bisector in triangle OAE. So I will present to you what is exactly angle bisector, and we will implement the angle bisector theorem in this right triangle, triangle AOE. Okay. So what is angle bisector theorem? Angle bisector theorem is true in any triangle So if we have a triangle ABC, that could be any triangle, this is triangle ABC, that could be any triangle, and we also have 9 segment AD. This is 9 segment AD that divides angle BAC, this angle, into two halves. Each half equals to theta. And this is exactly the definition of angle bisector. So here AD is angle bisector. I'll write it down. AD is angle bisector. So what is exactly is angle bisector theorem? Angle bisector theorem states that the angle bisector theorem, the angle bisector in a triangle so the angle bisector in a triangle divides the side that it is the angle bisector in a triangle divides the side that it is in our drawing. We have triangle ABC and AD is angle bisector. Angle bisector AD is each side BC. So we are relating to side BC. I can write here in brackets that we are relating to side BC because angle bisector AD each side BC, and angle bisector AD each side BC and divides it into two parts. The first part is BD and the second part is DC. And the ratio between those two parts is BD over DC. So according to angle bisector theorem, the angle bisector in a triangle divides the side that it is in a ratio that angle bisector AD divides side BC is BD over DC, as I've already mentioned. So add it in brackets, and that ratio is equal is equal to the ratio between the angles legs. And we are relating here to angle BAC. This angle has been bisected by angle bisector AD. So the angle that is bisected by angle bisector AD is angle BAC, and angle BAC is two legs, AB and AC. The ratio between those two legs is AB over AC. So the ratio between those two legs, that is AB over AC, equals to the ratio that angle bisector AD divides side BC. That is BD over DC. Very simple. Okay, I'll repeat again. The angle bisector in a triangle, that is to say AD, divides the side that it is, that is to say it is side BC, and divides it into two parts, BD and DC. The ratio between those two parts is BD over DC. So, and that ratio is equal to the ratio between the angles legs. And the ratio between the angles legs is AB over AC, that is to say AB over AC equals to the ratio that angle bisector AD divides side BC, that is BD over DC. In conclusion, AB over AC equals to BD over DC. Okay? Okay? I'll repeat again. The ratio that angle bisector AD divides side BC is BD over DC, and that ratio equals to the ratio between the angles legs, that is AB over AC, or AB over AC equals to BD over DC. So that is the angle bisector theorem. Now we will implement the angle bisector theorem in the right triangle AOE. So I will copy the right triangle AOE in a new page, and we will implement the angle bisector theorem in the right triangle AOE. Okay? So in the right triangle AOE, according to angle bisector theorem, we will get that the ratio that the angle with sector AP divide side OE is OP over PE, and that ratio, again, the ratio that angle with sector AP divide side OE is OP over PE, and that ratio equals to the ratio between the angles legs, that is to say it is equal to AO over AE. AO over AE. So we know that OP equals to 3 units, PE is PE, and it is equal to AO, that is 6 units, over AE. I repeat again, according to question number 2, OP over PE, it is the ratio of the angle of sector AP divides side OE, and it is equal to the ratio between the angles legs, that is actually AO over AE, according to angle of sector theorem. OP equals to 3 units, PE is PE, AO equals to 6 units. So in conclusion, according to question number 2, we found out that three over PE equals to 6 over AE. So here we will divide this equation by 3 and we will multiply it by AE, and we get that according to question number 2, 6 over 3 equals to AE over PE. Again, 6 over 3 equals to AE over PE. 6 over 3 is 2, so 2 equals to AE over PE. Here we multiply this equation number 2 by PE, and we get that according to question number 2, 2 times PE okay, so we found out that 2 times PE equals to AE, so AE is twice as long as PE. We define PE as A. PE equals to A according to our definition. Here PE equals to A according to our definition, and here also in the original drawing we know that PE equals to A according to our definition. So from equation number 2 we get that 2 times PE equals to AE. We can substitute PE by A and we get that according to equation number 2, AE equals to 2A. AE equals to 2A. Here, AE So we found out that A equals to 2A and P equals to A according to our definition. In the next step, we will implement the Pythagoras theorem on the same right triangle AOE. So I will copy triangle AOE in the new page and we will implement the Pythagoras theorem in this triangle AOE. We have already found out that AE equals to 2A, AO equals to 6 units according to what is given as the question, and here OE, from the drawing you can see that OE equals to 3 plus A. Again, OE equals to 3 plus A, so we can write here that OE equals to 3 plus A. Now we can implement the Pythagoras theorem on the right triangle AOC. On the right triangle AOC, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendicular. That is to say, we get here that here PT is a relation for Pythagoras theorem. Okay, according to the Pythagoras theorem in the right triangle AOE, we get that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is AE and the square of the hypotenuse is AE squared, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to AO squared. AO equals to 6, so AO squared is 6 squared, that is 36. The square of the hypotenuse is AE squared, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to AO squared plus OE squared. So AE equals to 2A, therefore AE squared will be equal to 2A squared and it is equal to AO squared. AO is 6, so AO squared is 6 squared, that is 36. And plus OE squared. OE equals to 3 plus A, so OE squared is 3 plus A squared. Okay, so in conclusion, we found out that according to equation number 3, 2A squared equals to 36 plus 3 plus A squared. Here we will open the brackets on both sides of equation number 3, and we get that according to equation number 3, 2A squared is 4A squared and it is equal to 36 plus 3 plus a square. 3 plus a square is 3 square, that is 9, plus a square plus 6a. So 4a square equals to 36 plus 9 is 45. So 4a square equals to 36 plus 9, that is 45, plus a square plus 6a. We subtract a square from this equation number 3, and we get that according to equation number 3, four a square minus a square is 3a square, and it is equal to 45. A square minus a square is 0, plus 6a. Here we divide this equation number 3 by 3, and we get it according to equation number 3. So 3a square over 3 is a square. That is equal to 45 over 3 is 15, plus 6a over 3 is 2a. So here we subtract 15 and also 2a from this equation number 3, and we get it according to equation number 3, a square minus 2a minus 15 equals to 0. Okay, so we have here a quadratic equation. In this quadratic equation, the coefficient a equals to 1, the coefficient b equals to minus 2, and the coefficient c equals to minus 15. And the variable that we are looking for in this quadratic equation number 3, is a, so x equals to a. And the general formula for solving the quadratic equation is x that is equals to minus b plus minus square root of b square minus 4 times a times c over 2a. So we put the data inside this equation and we find out the values of a, because x equals to a. So here a will be equal to minus b equals to minus 2, so minus b is minus b, that is plus 2 plus minus square root of b square, b equals to minus 2, so b square is minus 2 squared, that is 4, minus 4 times a is 1, and c is minus 15. Over 2a, a is 1, so 2 times 1 is 2. So actually, I found out that a equals to 2 plus minus square root of here inside the root we have minus 4 times minus 15 is 60, and 60 plus 4 is 64. So inside the root we left only 64, all divided by 2. So here a equals to 2 plus minus the square root of 64 is 8 over 2. So here we will have two solutions that are possible for a. The first solution for a is that a equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. So we found out that a equals to minus 3, that is a negative number, but you can see from the drawing that a is equal to side PE of the triangle APE. So A is a length, and as a length it must be a positive number. It can never be equal to minus 3, that is a negative number. So we cancel this solution and we left only the second solution, that A equals to 2 plus 8 over 10 over 2. 2 plus 8 is 8, and 2 plus 8 is 10, and 10 over 2 is 5. So we found out that A equals to 5 units. So we can write here that A equals to 5 units. If A equals to 5 units, 2A is 2 times 5, that is 10. So actually 2A is the length of side AE. So A equals to 2A equals to 10, and A equals to PE, and it is equal to 5 units. Okay? So in the next step we will find out the length of side BE. From the drawing it is very easy to see that BE equals to PE minus PB. I'll repeat again, BE equals to PB, again, B equals to PE minus PB. So BE equals to PE, P equals to 8, that is 5 units, minus PB. PB is the radius of the semicircle, that is equal to 3 units. So in conclusion, we found out that B equals to 5 minus 3, that is 2. So B equals to 2 units. So we can write here that B equals to 2 units. In the next step, we'll find out the length of side CE, or the length of line segment CE. So what is the length of side CE, or line segment CE? From the drawing, it is very easy to see that the length of line segment CE equals to AE minus AC. Again, AE minus AC equals to CE. AE minus AC. So CE equals to AE minus AC. AE equals to 2A, that is 10 units. AC equals to X, that is the line segment that we are looking for. So in conclusion, we found out that CE equals to 10 minus x. Here CE equals to 10 minus x. In the next step, we will complete the quarter circle to a circle. So we completed the quarter circle to a circle, and then we will extend line segment BO until it touches the circle. So here we will define the touching point of the extended line segment OB in the circle as point M. What is the length of line segment MO or OM? O is the center of the quarter circle and also the center of the circle itself. M is the point on the circle itself, and this is exactly the definition of a radius. So OM is the radius of the circle, that is equal to the radius of the semicircle, that is to say OM equals to 6 units. Because we know that the radius of the quarter circle equals to 6 units, and therefore the radius of the quarter circle is equal to the radius of the circle, and they are both equal to 6 units. Okay? Because of the fact that the quarter circle is part of the circle itself. Okay? And if the radius of the quarter circle equals to 6 units, it means that the radius of the circle itself must be also equal to 6 units because of the fact that they have the same radius. Okay, so in the next step I will present to you a new rule that is actually rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true. So according to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true. So actually we have the external point P, and point P is also the intersection point of those two chords. That is to say, the intersection point of the two chords is happening outside the circle. Okay, so we actually have chord AB. This is chord AB, that intersects with chord CD. This is chord CD. I repeat again, chord AB intersects with chord CD is point P. Point P is the intersection point. I write it down that point P is the intersection point of chord AB with chord CD. Actually, we have two different cases. We know that two chords of a circle can intersect with each other inside the circle, but the two chords of a circle also can intersect with each other outside the circle, and this is the case that the two chords intersects with each other outside the circle. That is to say, chord AB intersects with chord CD outside the circle at point P. So if this is the data that has been given to us, then according to rule number 3, PA times PB, PA times PB equals to PC times PD. I repeat again, we know that chord AB intersects with chord CD at point P. Point P is the intersection point of chord AB with chord CD, and the intersection point is happening outside the circle. In this case, then, according to rule number 3, PA times PB equals to PC times PD. Okay? So we can implement rule number 3 in our drawing. Because in our drawing we have chord AC that intersects with chord MB at point E again. Chord AC intersects with chord MB at point E. Point E is the intersection point of chord AC and chord MB. I'll write it down. In our drawing, chord AC intersects with chord MB at point E. Point E is the intersection point. I'll repeat again. In our drawing, chord AC intersects with chord MB at point E. Point E is the intersection point of chord AC with chord MB. Therefore, according to rule number 3, we will get that here EC times EA, EC times EA equals to EB times EM. EB times EM. I repeat again that according to rule number 3, EC times EA equals to EB times EM. Okay? So here EC equals to 10 minus X, EA equals to 10, EB equals to 2 units, and EM equals to 6 plus 3 plus 3, that is 12, plus 2 is 14. So in conclusion, in total, EM equals to 14 units. And 2 times 14 is 28, and 28 equals to 10 times 10 minus X. Here we will divide this equation by 10, and we will get that according to this equation, 10 minus X equals to 28 over 10 is 2.8. Here we will add X to this equation and we will subtract 2.8, and we get that according to this equation, X equals to 10 minus 2.8. 10 minus 2.8 is 7.2. So if I know that X, that is actually also equals to AC, it is equals to 7.2 units. 7.2 units, so in both methods we arrive to the same results. For X, that is AC, it is equals to 7.2 units. Okay, so we can write here that X that is also equals to AC, it is equal to 7.2 units. So we finish with the second method. In the next step we will summarize the lecture. We will start with the first method. Okay? So I repeat on the question of this lecture. We have here a semicircle inside a quarter circle. We know that side AO equals to 6 units. Side AC is tangent to this semicircle at this point. In this case is point D, and we want to find out the length of side AC that is equal to X, according to what is given us as a question. AC equals to X. So we want to find out the length of AC that is equal to X. So first of all, because of the fact that AOB is a quarter circle, point O must be the center of the quarter circle. And the angle AOB must be equal to 90 degrees. This angle is 90 degrees, it is the right angle. And because of the fact that point O is the center of the quarter circle and point A is the point of the quarter circle itself, that is to say AO is the radius of the quarter circle, because that is exactly the definition of a radius. So we know that the radius of the quarter circle equals to 6 units. That is to say, OB is also the radius of the quarter circle. For that reason, it will be also equal to 6 units, because the radius of the quarter circle is equal to 6 units. Again, because of the fact that it starts from the center of the quarter circle and ends at point B, for that reason, line segment OB is the radius of the quarter circle. For that reason, it is equal to 6 units. But OB, line segment OB, is not only the radius of the quarter circle, but it is also the diameter of the semicircle. So we know that the diameter of the semicircle equals to 6 units. Therefore, the radius must be equal to half of it. That is to say, the radius of the quarter circle will be equal to 3 units. That is to say, OP equals to PB equals to PD. All those line segments are defined as the radii of the semicircle. That is to say, they are equal to 3 units. Okay, then we connected together, joined together points A and P together. We joined together points A and P by a straight line, and then I presented to you rule number 1. According to rule number 1, the lengths of two tangents from a common external point to a circle are equal. So if we have this circle and we have point P that is an external point of this circle, and from point P we will draw two tangents to this circle. The first tangent is PA and the second tangent is PB. Then whenever you draw two tangents to a circle from a common external point of that circle, then the length of those two tangents will be equal to each other. In this case, PA equals to PB. We can implement rule number 1 in our drawing, because in our drawing we have the common external point, point A. This external point in relation to the semicircle. And from the common external point, point A, we have two tangents to the semicircle. The first tangent is tangent AO, and the second tangent is tangent AD. And according to rule number 1, whenever you draw two tangents to a circle from a common external point of that circle, then the lengths of those two tangents must be equal to each other. In this case, AO must be equal to AD, according to rule number 1. AO must be equal to AD according to rule number 1. But it is given us the question that the AO equals to 6 units. So we can write here that AO equals to 6 units. And from this equation 6 equals to AO equals to AD, we will derive that AD is also equals to 6 units. Okay, here AD equals to 6 units. Then we proved that those two right triangles can go into each other according to side rule. Why they can go into each other? Because of the fact that AO equals to AD, they are both equal to 6 units. AO equals to AD equals to 6 units. AP equals to AP, this is a common side that belongs to both triangles. And also OP equals to PD equals to 3 units. It is the radius of the semicircle. That is to say, all the sides of triangle AOP can go into all the sides of triangle APD. Therefore, those two right triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we will derive that those two angles are also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right triangles can go into each other, therefore the two corresponding angles must be also equal to each other. That is to say, those two angles must be equal to each other. That is to say, angle PAD must be equal to angle OAP. So if we define angle OAP as theta, if angle OAP equals to theta, then from this equation theta equals to angle OAP equals to angle PAD, we will derive that angle PAD is also equals to theta. This angle is also equals to theta. Okay? So those two angles, they are both equal to theta. Then we focused on the right triangle AOP. In the right triangle AOP, tangent theta equals to OP over AO. In the right triangle AOP, tangent theta equals to OP over OA. OP equals to 3 units. OA equals to 6 units. So in conclusion, tangent theta equals to 3 over 6. We divided both the numerator and the denominator of this side of the equation by 3, and we got that tangent theta equals to 3 over 3 is 1 and 6 over 3 is 2. So in conclusion, tangent theta equals to 1/2. Okay? arrive to the conclusion that tangent theta equals to 1/2. Then we join points O and C together by a straight line. In this way we created triangle AOC. We created triangle AOC, and then I presented to you the law of cosines, and we implemented the law of cosines in this triangle, triangle AOC. So what is the law of cosines? The law of cosines is true in any triangle. So in any triangle, triangle ABC, that could be any triangle. We know that side AB of this triangle equals to A units in its length, side AC equals to B units in its length, and side BC equals to C units in its length. Then, according to the law of cosines in this triangle, triangle ABC, we will get that C squared equals to A squared plus B squared minus 2 times A times B times cosine alpha. Okay? This equation is true in any triangle, so we implemented the law of cosines in triangle AOC. This is triangle AOC that I copied from the original drawing. Angle OAC equals to theta plus theta, this is 2 theta. AC equals to x, it is the line segment that we are looking for. AO equals to 6 units according to what is given as the question. And here, line segment OC starts from the center of the quarter circle, that is to say from point O, and ends at point C, that is the point of the quarter circle itself. And this is exactly the definition of a radius, that is to say OC is the radius of the quarter circle, that is equal to 6 units. Now we implemented the law of cosines in this triangle, triangle AOC. Okay, so here, according to the law of cosines, we will get that OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. OC squared equals to AO squared plus AC squared minus 2 times AO times AC times cosine 2 theta. OC equals to 6 units, therefore OC squared is 6 squared, that is 36. AO equals to 6 units, therefore AO squared is 6 squared, that is 36, plus AC squared. AC is x, so AC squared is x squared, minus 2 times AO times AC, that is minus 2 times 6x, times cosine 2 theta. Okay, so here we have 36 on both sides of the equation, so 36 will get cancelled. And what is left from equation number 1 after we cancel 36? What is left is actually 0 equals to x squared minus 12x times cosine 2 theta. We added 12x times cosine 2 theta to this equation, equation number 1, and we found out that 12x times cosine 2 theta equals to x squared. We divided this equation, equation number 1, by x, and we found out that here x will get cancelled, so we left in this side only with 12 times cosine 2 theta, and here x squared minus x squared over x is x. So in conclusion, we found out that according to equation number 1, 12 times cosine 2 theta equals to x. So in order to find out the value of x, the only thing that is left to do is to find out the length, the value of cosine 2 theta. In order to find out the value of cosine theta, I presented to you trigonometric identity for cosine 2 theta. The trigonometric identity is cosine 2 theta equals to 1 minus tangent square theta over 1 plus tangent square theta. We have already found out that tangent theta equals to 1 half. So we can substitute tangent theta in this trigonometric identity by 1 half. We did it, and we got that cosine 2 theta equals to 1 minus tangent square theta. If tangent theta equals to 1 half, tangent square theta will be equal to 1 half squared. So if it is 1 half squared, it is 1 plus tangent theta squared, that is it is 1 minus tangent theta squared, that is to say it is 1 minus 1 half squared. Okay, over 1 plus triangle theta squared. That is to say, it is 1 plus 1 half squared. 1 half squared is 1/4, so in the numerator we have 1 plus 1/4, and in the denominator we have 1 plus triangle square theta, that is to say 1 plus 1 half square, and 1 half square is 1/4. So in the denominator we have 1 plus 1/4. So 1 minus 1/4 is 3/4, and 1 plus 1/4 is 5/4. Here we have 4 in the numerator and 4 in the denominator, so 4 will get cancelled, and we left only with cosine 2 theta, that is equal to 3/5. So we found out that cosine 2 theta equals to 3/5. Now we can substitute cosine 2 theta in equation number 1 by 3/5. According to equation number 1, 12 times cosine 2 theta equals to x. Now we will substitute cosine 2 theta by 3/5, and we will get that according to equation number 1, 12 times cosine 2 theta is 3/5, and it is equal to x. So here 12 times 3 is 36, so this expression equals to 36 over 5, and this is the value of x. So we found out that x equals to 36 over 5 units, and 36 over 5 units is 7.2 units. So in conclusion, we found out that x, that is equal to AC, it is equal to 7.2 units. We finished with the first method. In the next step, I presented to you how to find out the length of line segment X according to the second method. In the second method, we used with all the fields that we have already found out in the first method. So here, this angle equals 90 degrees, this point O is the center of the quarter circle. We have already found out that the radius of the quarter circle equals to 6 units, and the radius of the semicircle equals to 3 units, so OP equals to PB equals to PD equals to 3 units. All the line segments are the radii of the semicircle, and we have already found out that those two right triangles can go into each other according to side rule, and from the fact that those two right triangles can go into each other, we will conclude that those two angles are equal to each other. So if one angle equals to theta, then the other angle must be also equal to theta, because they are equal to each other. Okay, so those two triangles can go into each other, and those two angles, they are both equal to theta. Then we did the construction. We extended line segment AC by a straight line, and we also extended line segment OB by a straight line until they intersect with each other at point E. Point E is the intersection point of the extended line segment AC and the extended line segment OB. In this way, we created the right triangle, triangle AOE. In the right triangle, triangle AOE, AP is angle bisector. Why? Because it divides angle OAE into two halves. For that reason, AP is the angle bisector, and we implemented the angle bisector theorem in the right triangle AOE. But first of all, I presented to you the term angle bisector. What is angle bisector theorem? According to angle bisector theorem, the angle bisector, so here we have triangle ABC, that could be any triangle. In triangle ABC, AD is angle bisector of angle BAC. Why? Because it divides angle BAC into two halves. For that reason, AD is angle bisector of triangle ABC. And according to angle bisector theorem, the angle bisector in a triangle divides the side that it eats. So the angle bisector AD in triangle ABC eats side BC and divides side BC into two parts. The first part is BD, the second part is DC, and the ratio between those two parts is BD over DC. And that ratio, so the ratio that angle by sector AD divides side BC is BD over DC, and that ratio equals to the ratio between the angles legs. We are relating to the angle that has been bisected into two parts, into two halves, that is to say angle BAC. Angle BAC has two legs, AB and AC. And the ratio between those two legs is AB over AC. So the ratio between the two legs of the angle that has been bisected, that is AB over AC, equal to the ratio that angle bisector AD divides side BC. And that ratio equals to BD over DC. So those two ratios are equal to each other. AB over AC, that is the ratio between the angles legs, equal to the ratio that angle bisector AD divides side BC, that is BD over DC. In conclusion, AB over AC equals to BD over DC. Okay? Then we implemented the angle bisector theorem in the right triangle AOE. So I copied the right triangle AOE in a new page. Here AP is the angle bisector of angle OAE. Why? Because it divides angle OAE into two halves. Each half equals to theta. So, therefore, because of the fact that AP is the angle bisector, we can implement the angle bisector theorem in this triangle, this right triangle, triangle OAE. So, according to angle bisector theorem, the ratio that the angle bisector AP divides side OE is OP over PE. And that ratio equals to the ratio between the angles legs. We are relating to angle OAE. And the ratio between the angles legs, angle OAE is two legs, OA and AE. And the ratio between those two legs is OA over AE. Okay? So those two ratios are equal to each other. The ratio that angle bisector AP divides side OE is OP over PE, and the ratio between the angles legs is OA over AE. Those two ratios are equal to each other. That is to say, OP over PE equals to AP over AE. Here OP is the radius of the semicircle that is equal to 3 units. So here we have OP is 3 over PE, and OA equals to 6 units according to what is given as the question. So in the other side of equation number 2, we have 6 over AE. Here we divided equation number 2 by 3 and we multiplied by AE, and we got that 6 over 3 equals to AE over PE. 6 over 3 is 2, so in conclusion, according to equation number 2, we found that 2 times 2 equals to AE times PE. We multiplied equation number 2 by PE and found out that according to equation number 2, 2 times PE equals to AE. 2 times PE equals to AE. We defined PE as A. Here PE equals to A according to our definition, and here also PE equals to A according to our definition. Then we substituted PE by A in equation number 2. So here AE will be equal to 2 times PE, and PE is A, so AE equals to 2A. So we found out that AE, line segment AE or side AE equals to 2A. While PE equals to A according to our definition, AE equals to 2A. According to equation number 2, A equals to 2A. Then I copied triangle AOE, the right triangle AOE, in a new page, and we implemented the Pythagoras theorem on this right triangle, triangle AOE. So this is the right triangle, triangle AOE that I copied from the original drawing. A equals to 6 units according to what is given as the question. A equals to 2A. According to what we have already found out, A equals to 2A. And here OE equals to 3 plus A. OE equals to 3 plus A. From the drawing you can see that OE equals to 3 plus a. Then we implemented the Pythagoras theorem on this triangle AOE. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the square of the hypotenuse is a square, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to a o square plus OE square. A equals to 2a, so a squared is 2a squared. OA equals to 6, so OA squared is 6 squared, that is 36, plus OE squared. OE is 3 plus a, so OE squared is 3 plus a squared. We open the brackets on both sides of equation number 3 and found out that 2a squared is 4a squared, that is equal to 36 plus 3 plus a squared. 3 plus a squared equals to 3 squared, that is 9 plus a squared plus 6a. Here we know that 36 plus 9 is 45. So in conclusion, according to equation number 3, we found out that 4a squared equals to 45 plus a squared plus 6a. Here we subtracted a squared from this equation number 3, and found out that 4a squared minus a squared is 3a squared. A squared minus a squared is 0. So in conclusion, according to equation number 3, we found out that 3a squared equals to 45 plus 6a. We divided this equation number 3 by 3, and we found out that 3a squared over 3 is a squared, 45 over 3 is 15, and 6a over 3 is 2a. So in conclusion, we found out that a squared equals to 2a plus 15. We subtracted 2a and also 15 from this equation number 3. And we found out that according to equation number 3, a squared minus 2a minus 15 equals to 0. So we have here a quadratic equation. The coefficient a in this quadratic equation is 1, the coefficient b is minus 2, and the coefficient c equals to minus 15. And the variable that we are looking for in this quadratic equation is a. So x equals to a. And the general formula for solving a quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, x equals to a, so here x equals to minus b, b equals to minus 2, so minus b is minus 2, that is plus 2, plus square root of b squared. B is minus 2, so b squared is minus 2 squared, that is 4, minus 4 times a is 1, and c is minus 15, over 2a is 2. So inside the root we have minus 4 times minus 15 is plus 60, and 60 plus 4 is 64. So we found out that a equals to 2 plus minus. Inside the root we have 64 over 2. The square root of 64 is 8. So in conclusion, we found out that a equals to 2 plus minus 8 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 2 minus 8 over 2. 2 minus 8 is minus 6, and minus 6 over 2 is minus 3. So we found out that a equals to minus 3. A is a negative number, but here, because of the fact that a is the length of side PE, it must be a positive number. A is a length, and as a length, it must be a positive number. It can never be equal to minus 3, that is a negative number. So we cancel this solution, and we left only with the second solution, that a equals to 2 plus 8 over 2. 2 plus 8 is 10, and 10 over 2 is 5. So we found out that a equals to 5 units. Here a equals to 5 units. If a equals to 5 units, 2a will be equal to 10. So 2a, that is AE, is equals to 10 units, and PE, that is A, is equal to 5 units. Then we found out the length of line segment BE. From the drawing, it is very easy to see that BE equals to PE minus PB. B equals to PE minus PB. PE equals to 5 units. PB equals to 3 units. This is the radius of the semicircle. In conclusion, B equals to 5 minus 3, that is 2 units. So here B equals to 2 units. Then We found out the length of line segment CE. From the drawing it is very easy to see that CE equals to AE minus AC. Again, AE minus AC equals to CE. Here, C equals to AE minus AC. AE equals to 10 units. AC equals to X. So in conclusion, we found out that CE equals to 10 minus X. Then we completed the quarter circle to a circle. We extended line segment OB by a straight line until it touches the circle at point M. Point M is the touching point of the extended line segment OB and the circle. And what is the length of OM? O is the center of the quarter circle. M is the point of the circle itself, and this is exactly the definition of a radius. That is to say, OM is the radius of the circle. That is also the radius of the quarter circle. That is to say, OM equals to 6 units because the radius of the quarter circle equals to 6 units. Then I presented to you rule number 3. According to rule number 3, if two chords intersect with each other outside the circle, then the following equation is true. Here we have chord AB that intersects with chord CD at point P. Point P is the intersection point between those two chords. So the intersection point is happening outside the circle. So in this case, the following equation is true, that PA times PB equals to PC times PD. Again, PA times PB equals to PC times PD. We can implement rule number 3 in our drawing, because in our drawing we have line segment chord AC intersects with chord MB at point E. Again, chord AC intersects with chord MB at point E. Point E is the intersection point of chord AC with chord MB. Therefore, according to rule number 3, we will get that EC times EA equals to EB times EM. EC times EA equals to EB times EM according to rule number 3. EC equals to 10 minus X. EA equals to 10. EB equals to 2, and EM equals to 6 plus 3, this is 12, and 12 plus 2 is 14. So in total, EM equals to 14. So here 2 times 14 is 28, and 28 equals to 10 minus X. We divided this equation by 10 and found out that 10 minus X equals to 28 over 8 is 2.8. Here we added to this equation X, and we subtracted 2.8, and we found out that X, the line segment that we are looking for, equals to 10 minus 2.8. 10 minus 2.8 is 7.2 units. So in conclusion, we found out that X, that is equal to AC, equals to 7.2 units. Again, X, that is equal to AC, it is equal to 7.2 units, and we arrive to the same result in both methods. Okay, X that is equal to AC, it is equal to 7.2 units. Okay, thank you very much.